Right, I'm making this video. I will have it on YouTube so you can speed it up, because it'll just be me working through things and showing you the process of how to do these. So it could be a bit clunky at places, right? And the reason I'm making this video is I just saw that in the 2023 paper, they had a rather unusual question, question 12, that the examiner's report says was quite poorly done. And I'm not really surprised. Okay, so the first thing is that I want to alert you to is a sort of standard question. And I just remind you that if you want to calculate any delta H, it doesn't matter really what it is, for any reaction, for a reaction. Okay, so it could be enthalpy of combustion, it could be enthalpy of formation. It doesn't really matter what they call it, right? It's based on the data you're given that you use. Okay, so if you're given enthalpy of hydration, or sorry, enthalpy of formation, then it's products minus reactants, right? So the sum of the enthalpy of formation of products minus the sum of the enthalpy of formation of reactants. If you're given delta CH, if you're given enthalpy of combustion, not that you want to calculate it, that you're given it, it's the total sum of the enthalpy of combustion of reactants minus products. And if you're given bond association enthalpy or bond enthalpy, right, again, you will use the bond dissociation enthalpy of reactants total subtract products. Okay, now looking at question 10 here, I just thought I'd point this out because they haven't actually told you what you've got, but you should be able to recognize the fact that all of these are reactions with oxygen, means they are all delta CH. Okay, and in that instance, it's reactants minus products. So, and you need to account for mole quantities. And the other sneaky thing here is they haven't given you the equation. So the standard enthalpy of formation of propane will be 3C plus, what is it, C3H8. 3C plus 4H2 gives you C3H8. And then you would add together as necessary. So 4 times minus 286, 3 times minus 394, right? And then over here you have minus 2220. So when you calculate that, it'll come out as, let's see, so it's so that's minus 2326. So that's reactants minus 2220. And that comes out as minus 106. So BB. Right, sorry. So that obviously should be letter B there, not the actual answer. All right. So just in case you get anything like that again, just look and see, are they giving you? It's most likely they'll either give you enthalpy of formation data, or they'll give you combustion data. So if it's enthalpy of formation, you'll have all of the substances you're interested in as products, and there'll be elements in their standard state. So it'll be the reactants on each side. And if it's enthalpy of combustion, you'll have something, the substance you're interested in reacting with oxygen. Okay. Now, question 12. I'm not going to go on to this in huge detail. Heterogeneous, you can look up yourself. Why is water present as a gas? And that's because of the temperature that they've given you, right? Its boiling point is greater than 100. Now, it's this one here, part B, which is dodgy. Just a standard enthalpy of neutralization. They did mention in the chief examiner's report that was poorly answered. So it's about producing 1 mole of water. And truth be told, I can't remember the exact definition, but it is related to the reaction of an acid and an alkali to produce 1 mole of water, right, in neutralization. Again, I would also have answered that poorly, so make sure you do your definitions. I'll maybe put a carousel together before. I'm going to just make a note of that now. To do a carousel quiz of the definitions before today. Actually, I'll do that today. Right. Now, this next part. So there's all of that stuff there, right? So the first part here isn't too unusual, right? So Q is equal to MC delta T question, okay? And you know that because they've given you C and they've talked about density of solution and all that, right? So we're going to say Q is equal to MC delta T. Now looking back, we're looking for a mass of solution or a mass of water. So here it is, right? So that's our M. They've given us C. Delta T they've given us as well. All right. So that is equal to 25 by 4.2 by 5.5, and that's going to come out as 577.5 joules. Okay, we're not going to worry about pluses or minuses at this stage. It is an exothermic process, but we'll worry about that later. So your final answer in kilojoules per mole will need to be 9. So we'll just put that in there so you know. Right, now delta H is equal to Q in kilojoules divided by moles. Now the moles we've got, so this is where we look at this. We've got 2.5 grams of potassium carbonate. So K2CO3, right, so they've given you the formula there. Its MR is equal to 39 plus 39 plus 12 plus 3 16s, which is 48, 138. So moles is equal to 2.5 divided by 138, which is equal to, oh, big number, 0.01811. I'm just going to leave that number in my calculator because I'm going to use it again, but actually it wouldn't round up like that. Let's keep okay, so that's how many moles we've got. Now it's Q in, now I'm going to convert Q to kilojoules because it's actually Q in kilojoules. Right, so that's equal to 0.5775 kilojoules. Okay, so delta H is equal to 0.5775 divided by the number I've kept in my calculator, 0.0181. Now I'm going to actually divide. Okay, so that comes out as minus 31.878, but I'm going to just check, give your answer to one decimal place. So 31.878 comes out as 31.9 kilojoules per mole. Okay, so nothing too weird and wonderful there. Now, what is weird and wonderful is this next bit, okay? So, right, now how do we go about this? So this is what I really want to focus the rest of this on, okay? They're saying blah, 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 use the value and value to calculate the enthalpy change. Now, I would say this has not come up for years, right? So we're going to just show you how it's kind of a mathematical thing. And I think I just want to give you a strategy if it comes up again at any point this year or next year. Right, so this is what we want, okay, as our final equation. What we have is, we have these two equations here. That's not what I want to do. Right, so we have these two here. Now, and we want them to, so we're going to manipulate these. So I'm just going to put in their values as we have them. And I'm going to just show you how to go about this now. As I say, this might be a bit fiddly. Right, so we have got delta H for that, minus 31.9 kilojoules per mole. Delta H for this is equal to plus 29.1 kilojoules per mole. Okay, so what we're going to do is we're basically going to double or halve or combine or switch these equations around, because what we ultimately want is this. Now, just looking at this, first thing is we need 2 KHCO3s on the left-hand side. Okay, so looking at that, we are definitely going to have to double this one, right? So I'm going to double that. And that will make that. So I'm going to make that 2, 2, 2, 2, 2. That will change this. We'll have to double this as well. So that'll be 29.1 times 2. 58.2. Okay. So that's now plus 58.2. I have a feeling I've made a mistake, haven't I? No. Oh, that's okay. Sorry, just checking. I thought, no, I'm on the right lines. Okay. So now the next thing to look at is that we have got K2CO3 on the, as a product. So we're going to have to flip that equation. So I'm going to just, right, reverse this. So that's going to be 2KCl plus H2O plus CO2 gives you K2CO3 plus 2HCl. And now the delta H for that will have to be flipped as well. So that's equal to plus 31.9 kilojoules per mole. Okay, now hopefully if we add those together, we will get the equation we're looking for. So let's just see if there's anything we can cancel out first of all. So our HCl's cancel out on both sides of the arrow. Our 2KCl's cancel out. We're going to lose a H2O on both sides. Lose a CO2. We're going to end up with 2KHCO3 gives you K2CO3 plus H2O plus CO2. And we're not using that. We're going to add those values together and delta H for both of them. So we've added the equations together. 58.2 plus 31.9. That's equal to plus 90.1 kilojoules per mole. Okay, and is that what we have? Yes. Okay, so it's a kind of a mathematical exercise. So you can reverse reactions and you have to change the sign of the delta H, or you can, if you double anything, then you'll have to double the delta H as well. And then when you add equations together, you can cancel out things that are on opposite sides of the arrow, right? And that'll give you your overall equation. Now, I think that's quite tricky. So I'm just going to go through a couple more that I found on another exam board's website, just to show you how that might operate in other scenarios. And then hopefully you'll at least have some strategy to use to approach this. So this one here is from AQA, MgCl, right? So let's write the equation first. So we've got MgCl gives you MgCl2 plus Mg. Now to make that balance, it's definitely going to be a 2 here. Okay, so you have to do your balanced chemical equation. Oh, this one isn't too bad actually, because actually this is just a straightforward enthalpy of formation calculation, which I didn't realize. I thought you'd have to combine things. So actually they've given you enthalpy of formation. So that's products minus reactants. The delta HF of an element is 0, because by definition you can't forming an element from itself in a standard state isn't going to have any enthalpy change. So actually in this instance, this is just product minus reactant, so minus 653 minus 2 times minus 113. That's equal to minus 427. Actually, no, that's an easy one. You don't have to combine. If they're all enthalpy of combustion or enthalpy of formation, you will not have to combine them like I just did there. It's only when they're different. Okay, so this one here, you have 2 enthalpies of combustion and then you have 2 enthalpies of formation, right? So this is not going to cut it. Okay, so this one here, thermal dissociation when butane forms propane, hydrogen, and carbon. So equation first, C4H10, C3H8 plus H2 plus C, and does that need any balancing? No, that's it. Okay, so one mole ratio for everything. Okay, in this instance, we're going to try and combine this. So first thing to note is we're definitely going to have to reverse that. So that's going to be C4H10 gives you 4C plus 5H2, because we need the C4H10 as a reactant. And that's going to be plus 125.2. So we're going to have that. Now we need C3H8 as a product. So we can probably use this one direct. We're going to add that in. Plus H2. I actually don't think we need all of the things they have there. actually, we don't need to use those. I don't know why they've given them to us. So actually, if we just add those two together, so if we have C4H10 gives you 4C plus 5H2, and we add 3C plus 4H2 gives you C3H8. That's plus 125.2 kilojoules per mole. That is minus 104.0. Add those. That's going to cancel to give you just one C. That's going to cancel to give you just one H2. So C4H10 gives you C3H8 plus C plus H2. That's 125.2 minus plus 104. Let's go to 21.2. Okay. Okay. Now let's have a look at this. Right. So here we want C4H, CH4 gives you C plus 4H. Okay, so again, we're going to have to reverse this one because CH4 is product here. So that's going to be CH4 gives you C plus 2H2. It's going to be plus 75. Now, products-wise, we have a C and a 4H. Now, the fact we have 4H means we're going to have to double that to get our 4H's. So that's going to give us 2H2. Gives you 4H, and that's going to be plus 436 by 2. That's plus 872. So actually, I think this is going to work out well. They cancel out. And CH4 gives you C plus 4H, and that's going to be plus 947. Okay. And here's another one. Again, we've got two enthalpies of combustion, but one that isn't, so we can't use our standard. Now, I'm not drawing any Hess cycles here because I actually think they will make your lives way more difficult, all right? So I think just use it as a kind of mathematical. Those of you who are doing maths, just think of that whole idea of combining equations and all that. I think it'll carry you through. Right, so again, we want enthalpy formation of carbon monoxide. We're going to have to write that. So that's C plus a half O2 gives you CO. Okay, I'm not going to bother with state symbols. All right, so this time, let's see, where's our CO? Okay, so we've got that, right? So we're probably going to have to divide it in two because we only want one CO. Okay, so we're going to have that. So let's put that in. So you've got a half C2H4 plus O2 gives you CO plus H2O, and delta H for that is minus 379 kilojoules per mole. Okay, what else do we need? We need carbon on the right-hand side. So again, we're going to have this. Okay, so we've got C plus H2 gives you a half C2H4. Right, so that's we've got our CO, got our C, and that is halved again, 52. It's plus 26 kilojoules per mole. And now what else are we missing? A half O2. So actually, if we just take the bottom equation and add it on, how's that going to work out? I think we'll add these together first and see what we get, because I think we have to reverse the other one. So we add those together, right? Cancel those out. we've now got C plus O2 plus H2 gives you CO plus H2O, and the overall change is minus 353. Now, so we've got a half too many O2s and we have a H2. So this is where it's going to come in. So if we reverse this one, so now if we make that H2O, gives you H2 plus a half O2, and that's plus 242. We add those together, that'll cancel out. That cancels out. That will cancel out to make that a half. Now we add them together. C plus a half O2 gives you CO, and answer is minus 111 kilojoules per mole. Okay. And last one is this one. No, again, they're not all combustion or formation. If they were, as I say, we just use those kind of standard equations that I taught you in class, and that come up in pretty much every past paper. Okay, so here we want a standard enthalpy formation of TiCl4, so we're going to have to write that. Well, that is Ti plus 2Cl2 gives you TiCl4. Again, leaving out state symbols out of laziness. Right, and we want, okay, so the first thing, we definitely want that top equation, okay, without anything changing. We definitely want the second equation because we've got Ti there. And I don't think we need that at all. That last one, I mean, we've no carbon. Oh no, we might. Let's add 1 and 2 together first of all. Okay, so what do we got? So C plus Ti O2 plus 2Cl2 TiCl4 plus CO2. Okay, so that's minus 232. And then we're going to add Ti plus O2, giving it TiO2 to it. It's minus 912. Okay, so we add those, we can cancel those out. That's it. So we've got C plus Ti plus O2 plus 2Cl2 gives you TiCl4 plus CO2. Okay, so what we've got that we don't want is C plus O2 gives you CO2. So if we reverse this one and then add it on, or you can subtract, but I think it's easier just, I don't know, I'm not great at the subtracting bit for some reason. Okay, so I'm going to flip that around. So that's CO2 gives you C plus O2. So the answer to this is minus 1144. Sorry, I forgot to do that. And then flipping that around, that is plus 394. If we add those together, cancel. Now we get our Ti plus 2Cl2, TiCl4. And that's minus 750 kilojoules per mole. Okay, that's that. If you need any help or anything, drop me a message. I can set up a wee Google Meet call or whatever. All right.